Hello friends, this is lesson 14 of NLP, Natural Language Processing, and today's lesson we are going to cover the following topics. Here, first of all, we will be discussing about unsupervised dimensionality reduction, then curse of dimensionality, dimensionality reduction approaches, principal component analysis, and we'll give some examples for them. Let's start with the first topic and see what is unsupervised dimensionality reduction. So, reducing the number of columns in your data set and not the number of rows, this is called dimensionality reduction, right? We have so many number of columns. If we have multiple number of columns, hundred of columns, or for example thousands of columns, so reducing the number of columns, not the number of rows. So this process is called dimensionality reduction. This you have to remember. And then transforming high dimensional space into low dimensional space by taking the most major features from the original data, right? So we have high dimensions, more number of dimensions, and we are reducing the number of dimensions by taking some major features from the original ones, right? For example, if we have 100 number of features, and from 100 number of features we will consider only 10 number of features, so that is called reducing the number of dimensions, right? Or for example, we will reduce it to 3 dimensions, 4 dimensions, 5 dimensions, from 1000 dimensions, hundreds dimensions. So the process is called dimensionality reduction. These features should be able to represent the whole. This is very much important, friends. Reducing the number of features, it is not like you simply reduce the number of features. If you are reducing the number of features, so the reduced features should be in a position to represent the whole data, right? If it is not able to represent the whole data, so this type of reduction is not useful, right? This is very much important. Like, it means you will be taking the major features, the common features, or we can say the key features, right? So those key features should be able to represent the whole data. If it is not, so your reduction is not correct. So the problems working with high dimensionality of data. If you have high dimensional data, what are the problems there? These are the problems, some of the problems I have listed, friends. First problem is data sparsity. The data is scattered a lot. So many dimensions are there. So this data sparsity we have. Then if we have data sparsity, what will happen then? The model degrades. The performance is reduced there. And also at the same time, what will happen? You know that overfits the model, right? And we have curse of dimensionality. Now let's see what do you mean by this curse of dimensionality. It refers to the phenomena that occurs when classifying, organizing, or analyzing high dimensional data that does not occur in low dimensional space, specifically the issue of data sparsity. So if we have high dimensional data and classifying that, this problem will happen. So we have, what do we have there? Sparsity of data is there. So we have so many number of dimensional data sparsity we have, right? This is called curse of dimensionality. More number of features, more accurate and high performance model. This is right, friends. This is very much important. You see, some people, they think if you are increasing the number of features, what you will get? You will get a high accurate model and a high performance model, a good model. The answer is yes for that. We can say yes. If you are increasing the number of features, you will be getting a good model, a high accurate model, and the model will be classifying and generalizing well the response value. But friends, this you have to remember, up to certain limit. This increasing the number of features, this is up to certain limit. It is not like keeping increasing the number of features. It has a threshold value. If you are increasing more than that, what will happen? Then the model will act in reverse order. Means the number of errors are increasing and the accuracy of the model reduces. right? This you have to remember, friends, right? If you are increasing the number of features, it is right, the model accuracy will be increased and model performance will be good, the number of errors will be reduced, but it has a limit. If it is crossing that limit or threshold value, then the model will be acting in reverse order. That point onwards is called curse of dimensionality. For example, if you consider only 5 features, but if you add another new feature, the 6th feature, what will happen? The model will act in reverse order. That is called curse of dimensionality, right? The model overfits and cannot generalize well, right? If we have curse of dimensionality, more number of features, or it exceeds the threshold value, then what will happen? You know that the model overfits and cannot generalize well. And now let's see dimensionality reduction approaches we have. These are the two approaches, feature selection and we have feature extraction. Most of the people or many students, they have this confusion, what is the difference between feature selection and feature extraction. And feature selections, it is nothing but the subsetting, or it is subsetting our column features and only using the base features from the existing one. For example, we are just taking a subset of the original set. You consider this set, we have ID, name, sex, date of birth, qualification, seniority, and then we have discipline, right? If you are taking a subset of that, we will consider only qualification, and then seniority and discipline. Maybe that is for identifying the salary, or maybe the response value is the salary. Only we are taking these 3 features. This is called feature selection. From existing one, we are taking the most common ones, or maybe base features, the keywords. This is called feature selection. But if you come to feature extraction, mathematically transforming our features set into a new extracted coordinate system, or we can say extracting new features from old ones, and those new features are called super columns. This you have to remember. Feature extractor, the model, for example, it will be calculating and finding the similarity or the relationship, the coordination between the features, creating new features from existing ones. That is called feature extraction. But in feature selection, we have already the features, just we will select the best features among them based on calculating the number of errors, like mean absolute error is there, mean squared error is there, and we'll see which features if we combine then we'll have less number of errors. So that is called feature selection. But here mathematically transform a new extracted coordinate system, or new features from old ones. Now what will happen here? What are the advantages in feature extraction? First, our models become much faster, right? Here in dimensionality reduction, if you are reducing the number of dimensions, what will happen here? Our models become much faster. You know that. Our predictive performance can give us insight into extracted features. And then what are the disadvantages? You know that we lose some of the interpretability of our features, as they are new mathematically derived columns, not our old ones. Because the number of features, you know that we will be losing the data, and mathematically derived columns, not our old columns. These are new columns, not our old ones. These some change, and then we can lose predictive performance also somehow will be reduced, because we are losing information. We have, like for example, we had 1,000 features, and from 1,000 features it is reduced to 100 features. Obviously what will happen, it will reduce the performance also. But you know that if we are developing a model based on 1,000 features, it is so much complex, heavy, the model, so the model will not be able to generalize well. We will be reducing to 100 features, then it will be taking less time, less space, and it is best model, we can call it. Now for that we'll be using principal component analysis. What is this one? Principal common linear transformation model. We have different models applying for reducing the dimensionality, friends, but in this case we will be using PCA, principal component analysis, for reducing the dimensions. So what is that? It is a linear and non-linear. PCA is a linear transformation used to transform high dimensional data into low dimensional. PCA is a method for transforming features into a that captures as much of the variability data as possible, right? PCA is often used as a dimensionality reduction technique for dense data. Dense data means linear data. If we have high dimensional data, so reducing the number of dimensions and making it all linear, that is called dense data. Let us see all these things practically, friends, here. Okay, we talked about dimensionality reduction, and then we said reducing the number of columns, not the number of rows. This is called reduction, dimensionality reduction. This you have to know. Transforming high dimensional space into low dimensional space by taking major features from the original. The feature should be, this is important, the feature should be able to represent the whole data, right? The common features or the key features what we take. And then we talked about curse of dimensionality. We said if you are increasing the number of features beyond the threshold value, then in the model will act in reverse order, performance will reduce, the number of errors will increase, right? Those things you have to know. And then we had data sparsity happens when moving to high dimension. If we have high dimensional data or space, there we have, and if we have sparsity of data, then we have these problems. Complexity increases, right? Space volume increases, data becomes sparse, accuracy reduces, and number of errors increases. That is up to a certain limit. This you have to, let me explain it here, friends. In model 1, if you consider model 1, we have only one feature. Then we'll create another model by considering two features, and you know that this model will generalize. Then we are increasing the number of features to 3 features, and you know this model is better than these two models. We have 3 features, and then we have 4 model, and here we consider only 4 features, and you know this is the base, right? But what will happen if you are keeping increasing the number of features and we reach the threshold value? Beyond that, curse of dimensionality happens here. If you increase like features, what will happen? This model will be the worst model. It will reduce the number of it will reduce the accuracy of model in number of features. Here in this point, curse of dimensionality will happen, right? Up to certain features, the model will be performing well. For example, here we will be considering only 4 features, like then we will consider 2 objects, orange, and we will consider ball, sphere. If we say sphere, yeah, orange is also sphere and ball is also sphere. Eatable, so orange is eatable, yes, but ball is no. But if we want to identify the ball, not the orange, so this should be no, because we don't want this orange. Here eatable is no, we don't want this. But ball, for ball we say yes, for ball we say no, but for orange we say yes. You see here, if it is 2-dimensional, you see these are linear, the data will be in this form. Change to 1-dimensional. Here we have 2-dimensional. You see the data sparsity is increased, If the number of dimensionals or increase to 3-dimensional, 4-dimensional, 6-dimensional, so sparsity of data will be still increasing. And for that we'll be using these two approaches, like feature selection or features by reducing the number of features. And feature selection, we see we are taking just subset of the original columns we discussed. Then in feature extraction we'll be creating new features from existing ones, and for that we'll be using a model called PCA, principal component, is used for reducing the dimensions or dimensionality of data. Let me give you an example here, and for that I'm using pandas. Let me read the data and this table, and I'm dropping the null values if there is any one, right? And we have two columns, labels, and these are the messages. The messages will be considered as features, and the labels are considered as our response values. And then from scikit-learn we'll import decomposition, right? This is used actually for creating a function here, like I say PCA underscore model. I will be passing here training data, testing data, and here the number of dimensions, how many dimensions I want, right? And PCA is equal to decomposition, and I'm calling a method called PCA, right? And this PCA number of components or dimensions, how many dimensions I want, and then PCA dot transform, and that will be transformed to those number of dimensions, right? The training data and testing data also I transform into less number of dimensions, and the result I return back to where I want. Okay, I executed this part, and now let's see before PCA. Let me compare these two, before PCA and after PCA, and let's see what is the model performance. So I'm using which model? Logistic regression. I will split the data into two partition, train and test, and then I'm using count vectorizer, right? And then okay, the data is split into two partitions. Here vectorizer is instantiated, and then the data is transformed into doc. Here the test data is also transformed, and the model is instantiated here, and the model is fit by training data, and here the model will be predicted, and I want to see the number of features, how many columns we have and how many rows we have, and at the same time I am printing the accuracy of my model. Let's see this, friends. Accuracy of model is actually equal to 98% or 99%, we can say. And how many columns we have? These are the number of columns, these are the number of columns, and these are the number of rows. We have 1393 rows in these number of columns. You see how many features we have, friends, so many features. And what will happen here, I am using PCA here, and I will be reducing the number of features from 7000 to 100. See, here we have 7000, actually 7500, and that is reduced to 100 features. And let's see again the result for this. Here I am calling my function. You know that, friends, here this is the function, and passing the values, training data and testing data, a number of columns, because this function, how many arguments it requires? Yeah, 3 arguments. So I'm passing 3 arguments from here. This is training data, testing data, a number of dimensions we want to number of components we want. So see, the number of dimensions reduced to 100, and we still get how much? 98%. You will say it was 99% and it is reduced to 90, how much? 98%, as we discussed here. Friends, this you have to remember. Yeah, this is the disadvantage, because we can lose prediction performance, because we are losing information as we extract fewer columns. The number of columns are reduced, friends, from 7500 to 100 columns, and we are getting, that's why 1% of accuracy is reduced. But you say this model is better because we have less number of features and it is taking less space, complexity is reduced, dimensionality is reduced compared to the first model. So I hope you understood all these things, friends. We talked about unsupervised machine learning, and then we talked about curse of dimensionality, approaches, feature selection and feature reduction, and the model which is used for feature extraction, PCA, and we gave examples for them. I hope you understood all these things. Thanks, friends.